So this week is a little different because there was no weekly work. So this week I'm going to try to pull together the first half of the course and lead us forward into the second half of the course. Of course, you obviously realize this is week 7. So we've got 5 weeks in the second half. I've gone at a fairly gentle pace, plus we've had a lighter week last week. So there's quite a few videos this week to watch, and I'll lead you through those in a minute. And this session, which I'll remind people of in just a second, is going to be going through the notes, and I'll just call your attention to a few things. So like I said, I'll just wait for 1 more minute while people dial in. Where were we? Okay, so let's get going. So in weeks 1 to 5, we mainly looked at sources of radiation and the governing electromagnetic field equations. In week 6, we went fairly swiftly through the beginning part of section 4. And section 4 was predominantly about the boundary conditions for the transmission of radiation and the reflection of radiation across boundaries. So let me scroll up to that section. And of course, hopefully you've downloaded the most recent version of the notes. I put up a new version this morning, actually, so there's minor changes. And I realize I'm flicking through the screen rather quickly. Actually, before we go on to section 4, I'd just like to call your attention to a few things in section 3. And this was based on the questions that came along in PHYS30141. So thank you very much for those of you who asked questions. And one of the key questions that was asked was about plasma oscillation. So let me run through the plasma oscillation derivation just one more time. Now remember, the idea of the plasma oscillation is to obtain a natural frequency for electrons which are displaced within an otherwise neutral plasma. So we had this formula for the square of the plasma frequency, and note this is the angular frequency. The angular frequency is proportional to the square root of the electron density. Okay, that's this number n. Now very often that electron density will be equal to the ion density for any ions which are left behind. So this n is the overall density of the ions and the electrons in the plasma. Now, we will see in a moment how we obtain this plasma frequency, and I'm just going to call your attention to how that plasma frequency is derived. But when we obtain this short form for the plasma frequency, you can see we can give it in a number of different ways. If n is in per centimeter cubed, then the plasma frequency is about 9,000 times the square root of n. If n is in per meter cubed, then the plasma frequency is 9 square root of n. Okay, so just remember that we'll be shifting between centimeter units and meter units quite often. And some of the examples questions and the weekly questions are deliberately made so that you get used to switching between those frequencies. And it's very important that you pay attention to the conventional units which we use, which can be either of those. So I'll just call your attention to that. Now, when we were deriving the plasma frequency, it does look somewhat artificial, this idea. This is figure 314 in the notes. And what we're trying to do in figure 314 is to illustrate an otherwise neutral plasma. So in all the regions of the plasma, left and right, we have a net neutral charge. In other words, there's equal numbers of positive and negative charges. And if we displace a layer of those electrons, a small layer of those electrons by a small amount, we are talking about moving all the electrons over, and we move them into a region that also has electrons and ions in it. So this layer that we're moving here is meant to be a layer of electrons that's been removed from this layer of positive charge on the left, such that it now overlies this otherwise neutral plasma. So this is a schematic picture that shows that. So this negative charge here is not meant to show all the electrons in the plasma, only the ones that we have moved. So therefore, the number density of the net amount of charge, the extra amount of charge that's been moved, is just the number density of the electrons and ions in the original unmoved plasma, which is why the number n appears here and in the positive charges left behind. So that's where this n comes from above. Okay, and we use this derivation which is a slightly artificial situation, to show that if I imagine now one electron moving on its own, we can see that the restoring force in the x direction, if it's displaced in the x direction, is proportional to the movement of that single charge. This idea of moving this layer of charge is somewhat artificial. But as we saw, when we thought about the passage of an electromagnetic wave, we imagine that the electric field is pushing trying to push the entire plasma backwards and forwards. So obviously here the polarization direction of the electromagnetic wave would have to be horizontal, and the propagation direction would be up from up, up and down. Okay, from up to down. So you imagine that when we have an electromagnetic wave whose frequency is equal to the plasma frequency, then the electrons will move in resonance with that electric field, that varying electric field. So that's piece number one that I wanted to call your attention to. Now, when we talked about collisions, one of the questions that was raised in PHYS3 was this drift velocity equation. And I realized that I should have put a little bit more detail into this discussion of how the drift velocity is attained. So the drift velocity is the average speed of the electrons in the plasma, or you might also think of these as being the average speed of electrons in a conductor, such as a metal. And we said that if we had an acceleration applied to those electrons, which is due to the electric field of some externally applied field onto those electrons, we could relate the acceleration and the collision time together to arrive at something which has the dimensions of a velocity. And I just said, without really justifying it, that the average velocity was equal to the acceleration times the time between collisions. So this, of course, needs a little explanation. So I've added an extra section down here. This is the derivation of that drift velocity. So the way we need to think about it is that it's not true that every single electron in between collisions accelerates from rest and then gets up to some velocity v drift and then experiences a collision that brings it back to rest. The value tc, this typical time between collisions, is the average time that an electron will travel for before it experiences a collision, either with an ion or with a lattice defect, if we're thinking of an electron in a conductor. So there will be a distribution of those times, and we expect that distribution of times, that each electron will have a different time t before it undergoes a collision. The average time that the electron spends in motion is tau c, the collision time, but there is a distribution, so very, very many of the electrons will quickly experience a collision in some time less than the collision time, and a very small number of those electrons will travel for a very long time before they experience a collision. So we can write down that the probability of a particular time, a collision time t, must be related to this average collision time, tau c, And this 1 over tau c here is obviously a normalization factor. And if you integrate this probability, then of course it should be equal to 1. So we can now work out what the average speed of the electrons in, and this is just the drift velocity we're trying to obtain. So this is going to be the average velocity of those electrons. Well, that's just the expectation value of AT, where A is the constant acceleration, regardless of which electron we're talking about, and T is the time that that electron travels for before it undergoes a collision. And we simply need to integrate over all such times with this probability distribution. And when we do that, okay, you'll be able to show for yourself that, hey presto, it's just equal to A times tau c. So that's where this Drude model relationship between the collision time and the drift velocity comes from. So hopefully that clears it up. So take a look back at the PHYS explanation and these notes again if you need any more thinking time about that. Okay, so that's the drift velocity. So as you can see, I'm going through a few different ideas. And so if you've got any questions about any of this stuff as we're going through, please ask in the chat. Now, the other thing I wanted to draw your attention to was the dispersion curve. So the first time you see these dispersion relations, which are also known as dispersion curves, they can be a little tricky. So I'm just going to go through this one more time. So figure 315 and 316 are meant to show different ways of looking at this dispersion relation. Now, a dispersion relation, just to remind you, is the relationship between omega and k. And the thing to hold in your mind is that an electromagnetic wave will have a fixed frequency, a constant frequency. So the right way to think about it is an electromagnetic wave which is being directed into some object. It could be a plasma, or later on we can see it'll be a waveguide. And we want to find out what the variation of wavelength is as a function of omega. So k is the wave number from which we can get the wavelength. So really we should think about this figure 315 as being the frequency is the independent variable and k is the dependent variable. However, we conventionally display it this way around, the way it's shown here, because we tend to write the dispersion relation in this form, which is equation 3,144. So be aware that the numbers have changed slightly because of that extra Drude model derivation of the drift velocity. So if you send any questions on PHYS, please refer to the latest 16th of November notes. So we've derived this dispersion relation, which tells me what the relationship between frequency and wave number is for a particular plasma frequency. And remember that the plasma frequency is determined by the number density of the free charges within the plasma. Okay, and of course we can invert this relationship to say that we have this dependence of wave number upon frequency. And of course you can see here, because this plus minus is telling us that I can have a wave moving either in the forward direction or in the backward direction in the plasma. And there are a number of different situations for different frequency and wave number combinations. So let's look at this figure 315 again. So figure 315 says that when the driving frequency, when the frequency of that electromagnetic wave that's trying to go through the plasma, when that value is very, very large, then the electrons are not really responding to the electromagnetic wave. So therefore the plasma appears nearly to be the same as free space. So the free space situation is this dotted line, okay? And you can see here that the actual omega curve, the solid line, tends to the free space situation for large values of omega. So you can see here that for large frequencies, we have the velocity is equal to omega over k, which of course is c. At lower frequencies, this solid line will deviate from the dotted line. And importantly, when the frequency is at the plasma frequency, so when the driving frequency is equal to the plasma frequency, then the wave number falls to 0 and the wavelength becomes infinite. And the physical interpretation of this is that the entire plasma is trying to move in synchronism with the incident electromagnetic wave. Okay, so it's slightly artificial to think of that electromagnetic wave as falling in some manner from vacuum onto a plasma that just starts with a finite density at some point. But it's a reasonable approximation. We can imagine a ramp up of the plasma density at some kind of boundary between the vacuum and the plasma proper. Okay, so the wavelength goes to infinity at this driving frequency. And of course, if the frequency falls below that, then there can be no propagation of the electromagnetic wave through the plasma, and therefore there is reflection. So an electromagnetic wave of low frequency falling on a high enough density plasma is reflected, and that's what this region between omega p and 0 is showing us. So another way to look at it is to look at the phase and group velocity in that plasma as a function of frequency. And I've just added this omega p here in the latest version of the notes to make it a little bit more clear. And we have the same basic idea. So rather than plotting omega and k, I'm now plotting omega and v, the velocity. And of course, you can derive the phase and group velocities. And this is a generally true statement that the phase velocity in any electromagnetic system where there is dispersion, that phase velocity is larger than the speed of light. And it's the group velocity which must be lower than the speed of light, and their product is equal to c squared. Okay, so Vp times Vg equals c squared. And we see the same basic idea at very large frequencies, both the plasma frequency and the group velocity, the phase velocity and the group velocity both tend to c. And at low driving frequencies, and I keep using that phrase driving frequency to remind us that this is like an incident electromagnetic wave being incident upon the plasma, the group velocity falls to 0 as the driving frequency approaches the plasma frequency. So as the wavelength grows to infinity, the whole plasma starts to oscillate. Starts to oscillate together, which is why the phase velocity goes up to infinity, and because of that, there can be no transmission of information from one end of the plasma to the other. So that's what this graph is trying to convey as an interpretation. Okay, now let's look at that in a practical situation, which I didn't talk about in the videos. So we'll scroll down and we'll look at this example about the Earth's ionosphere. So the first thing is to look at figure 318. And figure 318 shows the number of free electrons and ions as a function of altitude above the Earth's surface. So the Earth's surface is at the bottom of this y-axis, and as we rise up through the atmosphere, and the way to think about it is the conventional height of the Earth's atmosphere is something like 100 kilometers, above which there is this other tenuous region where it's not really an atmosphere as such, but the very rarefied air has been mostly ionized to a different density depending upon the altitude. And these different altitudes are depicted here, and we conventionally label the different ionization layers as D, E, and F. So the D layer lives down here at a lower altitude than the E layer, and the D, E, and F layers have different typical electron densities. So because they have different electron densities, we can then calculate different plasma frequencies. And in example 7, I ask you to explicitly calculate those frequencies. So I'll just bring up example 7 here. I think, yeah, here we are, the first question. So using the D, E, and F Earth ionosphere plasma frequencies given in the notes, calculate the electron densities in these layers and the resulting cutoff frequencies and wavelengths for transmission through these ionosphere layers. Okay, so let's look at what those values are. The typical D layer plasma frequency is 3 times 10 to the 5 hertz, about 300 kilohertz. The E layer has a higher plasma frequency, and the F layer higher still. So clearly the plasma densities also go up. Okay, and they should go up as the square. Sorry, they should go up as the yes, as a square of the plasma frequency. Okay, so as electromagnetic radiation is directed from either side of these layers, let's say from the ground, if we direct electromagnetic radiation upwards, and of course in section 2 we showed how we might do this, we can use an aerial that can drive a varying frequency, and we call these kinds of aerials that are probing the ionosphere, we call them ionosomes. So an ionosonde means an ion sounding device, okay? Because it's a sounding device is something that can probe the distance from the device that's doing the probing. Okay, so we can think of a sonde as being sonar in water or a depth gauge of some kind, but here we are launching electromagnetic waves from the surface of the Earth upwards, and we're seeing how long it takes for them to come back again. And from that time information, remembering that in the ordinary air, all these different frequencies more or less travel at the speed of light. They travel upwards to the ionospheric layers and then are reflected. So you can see that if the plasma frequency, if the radiation has a frequency below the plasma frequency, then it will be reflected. So let's look at that. So the D layer at the bottom here is the lowest plasma frequency. So if I launch low frequency radiation, it'll get reflected from the D layer and will come back first. The E layer has a higher plasma frequency. So if I launch higher frequency, shorter wavelength radiation, it will travel through the D layer, bounce off the E layer, and then come back. And that will take a longer time. So of course, by measuring the time, I can measure the altitude of that layer. And if I turn the frequency up even higher, and I launch it upwards, it will travel through both the D and the E layer and then be reflected by the F layer and then come back later still. And a sufficiently high frequency signal, okay, which means something above the highest plasma frequency. So let's go back. You can see that the highest plasma frequency is something like about 10 megahertz. So any frequencies which are much higher than that, say 20, 30, or 100 megahertz or so, will travel through all three layers and will go into outer space. Okay, so this is seen from the point of view of someone on the ground. Okay, so there are falling plasma densities above, but of course we don't see those. We can only measure the plasma densities below, because of course the ones which have a low plasma density very, very high up, we've already seen the reflected radiation from the lower layers. So we can only see it growing rather than shrinking. So if we see that pictorially, this is figure 319, you can see that long wavelength radio signals can travel up to the ionosphere, but then are reflected. So in the early days of radio operation, when our aerials were long wavelength, there were no radio signals which propagated outwards into space. But from the age of television onwards, and things like mobile phones, which have an even higher frequency, those signals can propagate through the ionosphere and then off out into space. So clearly this tells you that the signals that these navigation satellites, that the GPS signals, which are being used to help your smartphone figure out where it is, those frequencies must be greater than any of those ionospheric plasma frequencies. Okay, but therefore they must be larger than 100 megahertz. So you can only communicate with the International Space Station, with other satellites, with GPS satellites, with frequencies above about 100 megahertz. Okay, so that runs through the end of section 3. I'll just pause there for a second to give you a breather and have a drop of water myself. Okay. So whilst this is not strictly speaking part of the assessment for this course, I think it's a very good idea that you get to grips with the standard way that people label frequencies and wavelength bands. So at the end of section 3, I've given a listing of the different frequency bands which are commonly used. So these are the ones that everyone uses. And you can see here, I've talked about long wavelength, medium wave, and short wave radio. So these are our traditional longer wavelength conventional radio signals. So this is what you might call old-fashioned amplitude modulation radio, which is rarely used today. You can see that these signals span from rather low frequencies, high enough to encode audio. Remember, audio goes up to 20 kilohertz, but still quite long wavelength. We can encode audio over any of these bands from long, medium, and short wave. This is all amplitude modulated radio, which tends to be quite noisy, which is why no one uses it anymore. None of these frequencies or wavelengths can penetrate through the ionosphere. Now, you're probably aware that your ordinary FM radio, you think about Radio 1, which is 98.9 or 98.3 or frequencies around that, those are given in megahertz. So those frequencies at FM radio can penetrate the ionosphere. So your modern FM radio can go through the ionosphere, but it's still quite low frequency. Above this, when you want to have enough bandwidth, enough ability to encode higher rates of data, you need to move to the VHF and UHF bands. And the VHF band is the one that is predominantly used for television transmissions. Going to very, very high frequency, this is UHF. UHF sits between something like 300 megahertz to 3 gigahertz. And the thing I haven't said so far is that your ability to transmit and receive these signals scales, roughly speaking, inversely with the wavelength. And that's, of course, is to do with our ability to drive a signal in a receiving aerial. Remember, the electric field goes as 1 over r, and our ability to detect that varying electric field also goes as 1 over the wavelength, because we have at a higher frequency, we're using shorter antennas. So that's the basic reason why it becomes harder to receive at higher frequencies. Okay, there's also greater attenuation as well as a function of distance. So your very high frequencies, this 300 megahertz to 3 gigahertz range, is the one that's used for all sorts of devices. And you're probably aware that your mobile phone runs somewhere around the 1 gigahertz mark. Your microwave ovens run at 2 gigahertz, so they will interfere with some Wi-Fi signals. Your Wi-Fi runs at between 2 and 5 gigahertz, and so on. Okay. Now that UHF band overlaps with 2 other conventional bands, and these other bands are labeled L and S. And L and S are conventional labelings for frequency ranges which were used in radar. Now, those frequencies are also widely used for mobile phones, and your ordinary mobile phone, your smartphone, will usually operate in the L band region. Now, S band is extremely important technologically because your microwave oven uses an S band power device, and the waveguide that couples your microwave oven magnetron to the cavity is also S band. And S band is also used as the powering device for most radar. Think of commercial radar, airport radar, things like that. And S band structures, not just waveguides, but also accelerating structures, are the predominant devices used in particle accelerators. So, for example, if you undergo radiotherapy, the waveguides that couple the power sources to the radiation devices are S-band waveguides. Now, here's one I prepared earlier. Now, I'm going to go through this in more detail in the future video, but what I'm holding in my hand here, hopefully you can see that. I'll just stop the share for a second so you can see me more clearly, and I'll just pin myself so you can see me here. Okay, so this is waveguide. So you can see this is fairly hefty. All right. So we'll be in the next section, section 5, we'll be talking quite a lot about waveguide. And this is a section of 3 gigahertz waveguide, just so you can see what one looks like. You can see it's fairly hefty. This particular one is made of, I think this is aluminium, but it has a copper coating on the inside to improve the conductivity. And it also has brass flanges, which is why it has that yellow color, Okay, it has brass flanges for bolting the things together. So you can see that if I put several of these in a line, then I will have a tube down which electromagnetic radiation can pass. So hopefully I will just put that down there. You can see there's the tube, okay? And the idea of the waveguide is it will support an oscillating electric field for only certain frequencies. So the subject of the next section, section 5, will be about how we can describe the possible electric field configurations in such a waveguide. But hopefully you can already appreciate that the kind of wavelengths that can propagate down this waveguide must be similar in some manner to the opening size of the whole of this waveguide. So 3 gigahertz has a certain wavelength, and you probably won't be surprised to learn that the condition for which radiation can pass down this waveguide is when half a wavelength fits across the largest aperture, okay, rather than the smallest aperture, but we'll talk about that in more detail in section 5. So you can see there's a few interesting features here. Firstly, it's a solid piece of metal, so it's conducting all the way around, so it's not the same as a cable. So we'll also talk about transmission down cables. So here is an ordinary cable, okay? So you've obviously used these a lot before. So again, I'll talk about these as well. And this coaxial cable is a different sort of device. This is known as a transmission line when we think about how high frequency signals travel along it. So we can consider it as a transmission line because it has 2 conducting parts. It has a central pin and a central wire, and surrounding that wire is an insulating layer, and then there is another conducting layer on the outside, which of course is cylindrical in shape, okay, as it goes along. Of course, it's only cylindrical if the wire is straight, of course, okay? And the signal is maintained as a voltage difference from the central conductor to the outer sheath, as it's called. So, of course, we arrange this device so that there's only electric field and magnetic field in between the central pin and the outer sheath conductor. So that is an example of a transmission line. And we'll also talk about how transmission lines work to start with by considering 2 parallel conductors, but we'll see that this concentric device is basically the same kind of idea. And a crucial difference between that device and this one is, of course, here there's only 1 conducting surface rather than 2. So the question arises, how can one have a voltage which is varying in time in such a device? And of course, the answer is that the voltage can be different at different places along the waveguide at any given instant, because it takes time for that knowledge of the voltage to pass along the waveguide. Now, what's interesting about waveguides is the speed of the electromagnetic wave along the waveguide is lower than the speed of light. So it's a little bit like our plasma situation. But the reason the speed is lower here is that not because of there being a plasma, but because of the size of the aperture and the fact that when we apply boundary conditions, we arrive at a dispersion relation for the movement of electromagnetic waves along this guide. Okay, so the speed of electromagnetic waves along this waveguide depends on the frequency, and there is a cutoff, so it's like a plasma, and the speed of power transfer is lower than the speed of light, and the same thing is true for our coaxial cable. So this is S-band waveguide, and you can see S-band is something like 3 gigahertz. So in all of the examples I use, I will be talking about 3 gigahertz waveguide. Okay, so that's S-band. Now let's move on and we'll talk about scattering for a moment. So I'll skip through the bulk of section 4, as you will have seen from the videos, is based on material that you should already be familiar with. So I went through that fairly quickly last week, and I moved this week. And you should basically just look through that and just check through the examples and check that you're happy with the derivations. Now, in the video material for this year, I have put a fairly short form discussion of these boundary conditions. So I'm just scrolling down through them just to remind you of what they look like. If you are confused about any of the derivations or any of the discussion, I have put the complete set of lectures for last year onto Blackboard and onto the YouTube playlist as well. So please if you want to see a longer discussion of any of this section 4, then please go to the appropriate lecture. Oh, I'm sorry, I haven't shared the screen again. I do apologize. Well, I wasn't showing anything particular up till now, so let me just go back. So I was going through section 4, and I was just saying that if you have any trouble with the derivations as they've been given, please refer to the full form lectures, which are given at the bottom of the playlists, okay, on YouTube and also in Blackboard. Now let's go on to talk about scattering. Scattering is extremely important. So just to recap the idea of scattering, and I will call your attention to a couple of particular ideas. So the first thing to be aware of when we talk about the scattering electromagnetic radiation is, you can see here from our picture, this is figure 419, that that if I have low frequency electromagnetic radiation, where low frequency here means that the photon energy is small in comparison with the electron rest energy. If that photon energy is small, then there is no significant transfer of momentum from the radiation to this electron. So that circular thing in the middle is the electron being depicted as moving up and down because of the electric field in the incoming photons. So you can see that this process that we're talking about here, this is the classical scattering process, is when the incoming photons have low energy, which means much less than 511 keV. So of course, that allows us to have some pretty high frequencies. So all the frequencies that we've been talking about so far, which means even up to 10 to the 16, 10 to the 17 hertz, even up to things like X-rays, in other words, wavelengths of an angstrom or energies of about a keV, those are still low in comparison to the electron rest mass. So we can use the classical description that we've been using up till now. So that means that if incident radiation up to that sort of energy, which means, you know, X-rays of 110 keV or so even, we can think of those photons in purely classical terms, which means that the electrons, when they see that radiation, will accelerate up and down, and they will emit radiation which has the same frequency as the incident radiation. So that scattered radiation we see there will have that Hertzian dipole-like shape. In other words, where you have equal amounts of radiation being scattered forwards, backwards, and sideways, but of course not up and down in the direction of the acceleration. And the energy carried away by that radiation, of course, it contributes to a reduction in the incident radiation intensity. And this is the idea of scattering. Now, when we go through our formula for the amount of radiation, it's exactly the same formula for what we had for our atomic model, our model for the motion of an electron under the action of that incident electromagnetic field that's varying. And we saw that there were 3 separate cases. Okay, so remember, all of these formulae are for the scattered radiation power, which is scattered by a single electron. So if I have an electromagnetic field of strength S, the power P here is the power radiated by one electron, which is sat within that electromagnetic field. And by comparing the incident radiation power S to the scattered power P, we can see, if we think about the units of that the relationship between P and S has units of area. Okay, so that's why we call it a cross section. It's the effective size of that electron to the radiation field that the electron is sitting within. So because that cross section has units of area, it must clearly be relatable to some dimension of the electron, and that's where the concept of the classical electron radius comes from. And now we saw before that the classical electron radius could be interpreted somewhat by thinking about the amount of energy that is contained in the electromagnetic field around an electron. Now we remember that calculation is physically false, but we do arrive at a value of R0, which we can use in this equation for sigma. There's a couple of other factors there as well. And that's why we use this factor 8 pi R0 squared over 3 to convert from that characteristic size of the electron, the classical electron radius, into this effective cross-sectional area. Now, if you look at the videos, you will see that there are 3 interesting cases, and all 3 of these cases involve frequencies omega, which are way, way, way less than that frequency would have to be for the photon energy to be similar to the electron energies. So these are all way, way, way lower. Okay, so there are 3 frequency regimes. The first one is that very low frequency regime, where we see that the resonance of the electrons, here we think of the electrons as being bound to atoms, and therefore they have some resonant frequency. When we're way below that resonant frequency, we see that the variation of cross-sectional area with frequency goes as frequency to the 4th. And that, of course, is what gives rise to Rayleigh scattering. At medium frequency, when the frequency is equal to the resonant frequency, and again, this resonant frequency is way lower than the frequency which would correspond to the electron rest mass, which is way higher than this. Okay. Then we have resonant scattering, and at very high frequencies, we can think of the electrons as not being bound to the atoms at all. And then we approach a constant value for that cross-section area, which we call the Thompson scattering cross-section. So the Thompson scattering cross-section applies equally well when we have electrons bound within atoms or whether we have free electrons. And this is the reason, of course, in our Compton scattering formula, that we don't need to care about whether or not the electrons in our material are bound or not. Okay. Already, with quite low photon energies, so here we remember that our condition for Thompson scattering is a photon energy which is way above the resonant frequencies of the atoms, which means something above an EV or so, but lower than the rest mass of the electron, which is photons of energies of 511 keV. Right? So this region here where Thompson scattering is valid spans an enormous range from ultraviolet light right up to quite hard X-rays, where hard X-rays means something like 10 to 100 keV even. Once you get up to the tens to hundreds of keV, then the photon energy becomes comparable to the electron rest mass, and then we expect a shift from this Thompson regime, when there is no transfer of momentum from the photons to the electrons, to the Compton regime, which of course we talked about in the first year. The Compton regime is when there is an appreciable, a significant transfer of momentum from the individual photons to the individual electrons. And when we work that out, now again, this is not an assessed part of this course, but clearly we want to know about it, right? There must be a parameter, which we call the recoil parameter, which tells me how much that effect is, how much that transfer of momentum is. And if you look at the particle physics aspects of this, you can draw a Feynman diagram in each of these terms that appears in this equation here. This is equation 4120. We can relate each of those terms there to particular terms in the Feynman diagram. And what this lets us do is we can draw a parallel between this particle physics calculation and our classical calculation, and we can arrive at the Compton cross section, and it will be smaller than the Thompson cross section. So our Compton cross section turns out to be lower than the Thompson cross section, and takes account of the fact that the recoil results in a lower photon energy from the scattered photons compared to the incident photons. And because that photon energy is lower, one might expect that the total amount of scattered power is also lower. That's why the Compton cross-section goes down. So you can see that's our difference between Thompson scattering and Compton scattering. In Thompson scattering, the photon energy that's scattered is equal to the incident energy, whereas in Compton scattering, the photon energy is reduced. So of course, in first year, what you derived was how the photon energy, the scattered photon energy, varies as a function of varies as a function of scattered angle. Now, we would also expect that the rate of photon production should also vary as a function of angle. So in Thompson scattering, so let's show that graph. That's what figure 422 is showing. So you can see here that the dotted line is the rate of Thompson scattering as a function of scattered angle. And the difference between this plot, this dotted line, and our Hertzian dipole is our Hertzian dipole plot was for polarized incoming photons, whereas this dotted line is the averaging out of that power if I rotate the incoming polarization direction. So if I average that out, my donut with a zero emission in one direction is smoothed out. So I still have equal numbers of photons going forwards and backwards, but now I have some photons going up and down, and I also have the same number of photons going in and out of the page, as we see here. With Compton scattering, which is the solid line, the rate of photon scattering is changed. So the amount of power that goes forwards is increased compared to the amount of power that goes backwards. And of course, this is what you might expect, because the photons which are coming in from the left-hand side are more likely to produce photons which are going forwards than photons which are going backwards. So that's the difference between Thompson and Compton, and also the difference between Thompson scattering, which is for unpolarized photons, compared to the Larmor formula for our Hertzian dipole, which was talking about polarized photons. Okay, so make sure you know the difference between Thompson scattering and Compton scattering. But that's the physical interpretation of those things. Okay, so I think we've more or less run out of time for today. Now, there's one other thing I want to call your attention to just before we finish. I don't know if anyone had any questions. I'll just check on the chat. Okay, there's one extra thing I want you to look at quite closely, and this is the this section of Lilly nuclear physics, which I've put on Blackboard. I'd like you to work through carefully this calculation in question 3 on the week 7 problems. Now, this is meant to show that what we were talking about is the rate of scattering from a single electron. And of course, very often we talk about scattering from large numbers of electrons in things like plasmas or things like gases. So to help us understand that, I'd like you to work through on question 3, which is to look at the scattering of 10 keV photons going through air. And next Monday, I'll go through how to do this calculation and to talk you through this relationship between the microscopic cross-section sigma and the macroscopic cross-section capital sigma. But I'd like you to read through Lilly Nuclear Physics section 1.6 before you do that. And then in question 4, now this is the same as in the example sheet, but I will go through that question in particular. We're going to talk about how to diagnose a fusion plasma, and we'll talk about that relationship between the plasma frequency and the cutoff frequency, and also about the scattering rate of photons passing through a plasma, because I'll just finish off by talking about one more thing, which is I'd like you to look carefully at this figure at the end of section 3. Where have I got it now? Here we are, the question at the end of section 3, where I show how the critical wavelength, which is the boundary between reflection and transmission in a plasma, okay, I'd like you to calculate that line, and I've put the 3 ionospheric plasma densities and cutoff wavelengths as red dots, I'd like you to specifically calculate those values so you can show for yourself you can calculate those numbers. And when we have shorter wavelengths, you can see that we still have scattering, even though we have transmission. So our plasma calculation talks about the boundary between reflection and transmission, but when the photons can penetrate the plasma, when they're not fully reflected, they will still scatter due to the re-radiation by the electrons moving as the photons are traveling through the plasma. So we'll talk about that next Monday, and I think that's quite an important jumping off point to then talk about passage of radiation through waveguides. Okay, hopefully that's all been reasonably clear and I haven't gone too fast. If you have any follow-up questions, please ask them on Piazza and or have them ready to ask in next Monday's session, or of course you can also dial in on Wednesday for the one-to-one session. Okay, have fun folks, and I will talk to you all next Monday. Cheers all.